All right, day 8. I have slept a lot, and I'm just about recovered from the Christmas party now, I think, apart from some slight residual lip chapping. No, not like that. Just it was cold and alcoholic. Anyway, I should get started. Um, all right, so we have here what I believe to be a graph problem. Um, Now there are a few. Oh, okay, fine. Let's try again. Great. So there are a few ways you could think about solving this. And the sort of there is what I believe to be a correct way. Let me check my audio settings actually. Yeah, I'm right. There is what I believe to be a correct way, which is however, the correct way may also be a trap. So um, there's that. Still, the correct way, I believe. You build a graph. Yeah, it's a graph problem. And actually, yeah, yeah, okay. So they're not all the same letters. Fine. Um, yeah, and so you end up with something like this, where I suppose it would be sensible to put them going downwards, right? Since we can then have left and right be really left and right. So in this one, we're supposed to go right, then left, then right, then left, then right. So we've got a sort of alternator or an oscillator, I suppose. Um, and then we essentially just keep doing this. So B, D, 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 E, E, E. Though actually, we can't model it like this because it's a graph, not a tree. So I will have to mess this up at some point. Let's say this is left, this is right, and this is left, and this is right. That's from B. C, we've got, well, those are going to have to start messing up. So for C, the left one is Z, 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 and then it's G, G, G. And I could do the others, but it doesn't really matter because we're supposed to go right. So let's go right, then left, and then we're at Z. I don't know why I'm saying Z. I'm British. I should say Z. Z. We end it with Z. So that's all fine. We don't need to build the whole graph, but in theory, we would build the whole graph, and that would make traversing it very straightforward. Um, Now, some traps here is if you model this as a list, you have to go through all of the list for every jump around the loop, and there could be, given the input, which is quite long, and in any case, the things we know about these puzzles, going through the list each time could take a long time. So that there could be a billion steps, and we'd have to go through the list each time, so we'd end up with a big complexity, time complexity. Um, there's another way where you model it um, with essentially you could implement a structure like this with a dictionary. So there's sort of let's call this the first one I said, or rather the second one, the really slow one. Let's call that slow solution. Let's have this be in blue. Let's call that the slow solution. List iteration. Then there's like a semi-fast, which may also be, well, actually just call it fast dictionary, where you implement this as a dictionary with the keys being the name of this, it's the name of the cell, the name of the location, and then these are it's just a tuple of things, and you end up looking up in the dictionary each time. So you take left and you get B, you look up B, you get, yeah. So it's fast. And then there's fast B, which is you build a graph. So you actually create an object A, which is a pair of references to other cells. So no dictionary, and you build a sort of graph proper. Let's look at it with this other example as well, so you can see how this then plays out. So here we've got an A. We've got a B and a Z. Let's color this back in black. And then the B itself has a and a Z, and the Z just goes back to itself for both. Which, you know, we should never have to go anywhere from Z anyway. So in this case, we have a different oscillator here. I don't know if oscillator is the right word. So here we go left, which I'm not going to use the colors because I think we will repeat. So I'm going to use this diamond instead for our counter. So we start off at A, we go left to B, we go left to A again. And actually, if I do this properly, you'll see what I mean. Yeah, so not modeling it as a tree, in fact, modeling it as this. Yeah, so okay, so we start off at A, we go left, we get to B, we go left, we get to A, we go right, we get to Z. So we kind of go around the graph. Walk it, I suppose. And then we just got to do it with this. I'm tempted to build the graph. Here's my guess, which is totally metagame level. I believe that building the graph will be seen as the nicer solution, and so in principle, then be rewarded. In any case, hopefully it won't take that long to do either way. We may have to throw everything away for step 2. So I think we just got to accept it. I mean, if we look at what could happen, maybe. Okay, so possible steps 2. Step 2s. These words have some meaning, and that changes the order of the sequence. In which case, we'd need to then do some magic around finding the right place to go in the graph, and then all of this graphiness would be pointless. Maybe, probably just still sort it out anyway. Or there's some change to the meaning of this or this that then causes us to have to loop a lot of times. Now, the way you might be able to solve that is maybe you can make direct connections between lines in the graph. So, you know, we do know that if we take if we're at A and we have the string, if our next sequence is going to be something like LLR, we know that if we have A plus LLR, it's always going to get us to a particular node. Let's find out what node that is. So A left, and then D. Well, we should get back to D. So we're always going to end up here with that. So we can skip some of the work here if we know the sequence that we're dealing with. Now, in principle, I suppose um, in theory that's true anyway, the whole problem. So I'm not really sure if that helps us, but I think if we end up with repeats in the place that we are, and we might be able to resolve it using some dynamic programming, where if we've seen this combination of things before, we're going to be able to skip some of the work. But yeah, it's a big guess. So let's not assume it. Let's start thinking about our plan. So we're definitely going to need to have a state. Well, in fact, we're going to need to have a cell. A cell has a left and a right, and these are also going to be cells. And what else does it need to have? I guess maybe it should have a name or something. Yeah, that helps us build out that. And we're also going to need to have, I would say it would be, oh gosh, it would be prudent to have a, I don't even know if oscillator is the right word, but let's go with it. It's going to have a, there's, it's going to have a, let's go with index, which is going to be the current place we are in there. And that's it, I think. And then we can have some, why it's this again. We can have a advance, and we can have a current. Let's go with a string. Let's go with none. Let's make it stateful. And then we can have a follow, which takes a string. And the string is really just going to be L or R. I'm just trying to avoid having to have a special treatment for that. Oh, but actually, that won't work because it doesn't know about other cells. So actually, we need to move to a state. Now, so a state has a current cell. It has a has an oscillator. Or in fact, we don't really need. No, we do. And then we can have a we can have an advance, and then I mean theory that, and the algorithm there is going to be, how are we going to find AAA? Just need to make note of it when we get it. Starting at AAA. Yeah, so that's fine. The others appear to me to be trivial. How long is this? Gee, look at my input. 796. Okay, fine. I think I will pass them just for convenience. Okay, so on top of this, we then need a line and a compute. And then we're going to have a well, we need a plan of action. So cell, isolator, methods, state, advance, steps to ZZZ, pass line, compute, and then we win, I think. Great. Okay. I think we're good to get started. I think step two will probably be a real punchy one today. So let's watch out for that. Back on my nice setup now, as you probably may have noticed. I think I'm going to lower the screen a little bit. There we go. All right. I got an amusing comment. I actually realized I'm using 3.12 alpha. I need to stop that. I got an amusing comment yesterday on day 7 video saying good luck with today's puzzle. So uh, I hope it was earnest. Okay, let's get started. Need to remember how to do that. Is that right? Well, we'll find out, won't we? I don't know why I'm so quiet today. Clearly, my brain is not working properly. Okay, let's try that again. Great. Let's go to current. I guess that as well, right? Okay. Okay. Hmm. Well, we don't have a reference to it yet. Okay, that's going to be a problem. Um, hmm. Okay, well, we can do it in two passes, right? That's probably the most straightforward to do it, and I'm already sort of let myself get taken by surprise for this. So yeah, we can do it in two passes. Hmm. So first should be B cell. Then it should be A cell. No, the oscillator is LLR. Yeah, then it should be, yeah, so it should be A first, then B, then A, then B, then let me get my diagram up. Okay, so A first, which we've already counted, B, A, Z. That's not 6 steps. 6 steps. Okay. Uh, B, A, A both goes to both of A. Yeah, I've got this. Let me switch back to my diagram. I've got my diagram wrong. All right, so this is wrong. So A actually goes to B, both goes to B. B, left goes to A, right goes to Z. Fine. Okay, so step one, left, left, right, left, left, right. Yeah, okay. So the steps are, so it's left, left, right. Yeah. A, left, B, B, left, A, right BBB, left AAA, left BBB, right ZZZ. Okay, right. So that's what it should be. So starting off at A, then B, A, B. Sorry, switching back to my code. A, yeah, B, A, B, A, B, Z. Incorrect. Where's it failing? Back at A again. We're not advancing. Oh, we're not switching. We're not switching. That's why. Okay. All right. First mistake. Fine. All right, back to the plan. Great. Okay. Actually, we don't even need this. Well, I'll save this. Okay, so cell equals, so it's actually stating line 0 to 3. Okay, great. That it? Yeah. And I need the cell dict as well. Okay, fine. Um, okay. Messy. Come on. Mm, wrong one. Oh, one. 2, 3. Are we doing well? Do I win? Okay, let's find, let's find out. State steps to end. No, no, not 0, not 0, not 0 at all. Oh, no, wait, I can set this up. 2, that's correct. Let's try with the second trial. 6, okay, now we're good. Input then, that, and it's already kind of slow. All right, let's find out whether we win this round. I do, okay, 2608. So a gold round, not too bad, but a few unforced errors there. Let's try step 2. Sandstorm is upon you, and you aren't any closer to escaping the wasteland. You had the camel follow the instructions, but you've barely left your starting position. It's going to take, oh, significantly more steps to escape. What if the map isn't for people? What if the map is for ghosts? Are ghosts even bound by the laws of space-time? Only one way to find out. After examining the maps a bit longer, your attention is drawn to a curious fact. The number of nodes ending with A is equal to the number of ending with Z. If you were a ghost, you probably just start at every node that ends with A and follow all of the paths at the same time until they all simultaneously end up at nodes that end with Z. For example, here there are 2 starting nodes, 11A and 22A, because they both end with A. As you follow each left-right instruction, use that instruction to simultaneously navigate away from both nodes you're currently on. Repeat this process until all of the nodes you're currently on end with Z. If only some of the nodes you're on end with Z, they act like any other node and you continue as normal. In this example, you'll proceed as follows. 11A, 22A. Choose all the left paths. You choose all the right paths. Oh, see, they don't multiply out. Well, that's good. Okay. So how many end with A? That's a that's a big question. How many end with A? How many end with Z? I think I can permit myself a little bit of regex here to check how many there are. 6. Oh, well, that's not so bad. That's not so bad at all. 6 and 6 and with Z. Oh, that's fine. Unless it's a lot more steps, which it probably will be. It's already taking, well, most of that time is probably printing, but it's already taking a while. So we've got 6 sort of heads to move between, move along. It's going to take a lot more steps. So we're probably going to have to do some performance tuning. I do have a notion as to how I will do that. Okay, let's let's have a bit of a diagram about this. So, and these are the A's, and these are the Z's. So keeping track of a number of different heads is no problem, right? We just execute them all essentially in a loop. That's going to be no big issue. I don't think. Just a bit of reprogramming. In terms of if we do need to speed up the process, then we could start to make some links directly between nodes on this graph. So to do that, the thing I'm hesitating over is how long do we want these jumps to be? Okay, so there's one question, right? Have we been on this node before? If we've been on this node before, then we can sort of ask it, these are my next, like, have you seen what happens if we go left? Have you seen what happens if we go left, right? Have you seen what happens if we go left, right, right? But we'd have to find some way of updating it in that case. Or we could just always say that we care about the next 3 and we're just going to keep track of like essentially 3 many. Or the last 10. That should take things down by a factor of 10. Okay, let's just diagram this out. Horrible. Okay. This may take a while. Hmm. Just thinking about detecting, like if we've been somewhere before. Anyway, I mean, just the diagram will help. Okay, to do B. Fine. No, that's not right. Wait a minute. I just realized there's a tool I can use for this. What have I messed up in the syntax here? Ugh, semicolons? Ugh, what is it? Why aren't you loading? Why? What's wrong with you? No, no. Not this page again. Oh, it's just eating my browser is what it's doing. It's two. It's okay. It's two. Fine. I can deal with that. No semicolons required. What's wrong with that? No, no. Stop it. Stop this. God, what a nightmare. Okay, now I need to label the edges. How do I do that? Okay, I can do that. Great. Now, all the way back. It looks so nice. Why did I do this? Is this good? Is this helpful? No, it's terrible. Okay, that was a huge waste of time. Go back to doing it manually, since clearly can't beat humans at this. 22Z, which goes all the way back to here. So that's a cycle, right? 22B, 22C, 22C to 22Z, 22Z to 22B, and then X just goes back to itself. Okay, so in this picture, we have, I guess we'll have a green and an orange counter, and we start off here and here, and we go left and right. No, just don't do that. I don't remember this being so annoying. Okay, so one on A left, and this one left too. Then we go right. There's just no need. There's just no need, is there? Then we go right. Then we go left. Now 1Z left I didn't actually do for some reason. So we're going left. Just remember that. Left. Okay. 11Z to 11B left. It's back up. And right is to here. So we're going left, which is back here. Left is here. Oh, okay. I'm starting to get an idea now. We can keep track of the Zs. When we hit a Z, that's when we really care. So we want to know the nearest path to every Z and how many steps that's going to take to get to the next Z. Yes. So that if we then calculate steps from each cell to the next Z, that will help us. assuming that the cycles are actually legitimate and they're always the same. Well, yeah, I mean, they must like if you, hmm. Okay, all right. Well, let's keep track of that idea. Where were we? We just went left, I think, now right. Left again. Right. Left. I know we were just on it. Yeah. We might have been on that before. Okay, so what we fall into is a each counter can be represented as a cycle with a sort of starting bit. So let's start with the A. Now, a cycle is 1 1A left, 1 1B right, 1 1Z left, 1 1B right, and then it continues. So we can define the cycle here like this. Now here we start here, we go left, so we're at 2 2A, 2 2B, yeah, left, right, left, right, left, right, left, and I mean it continues. So we've got 2 2A, B C Z, B C Z, B C Z. And so what we want to end up with is all on the Zs. So we've got a simultaneous equation, right? 1 plus 2x equals 1 plus 3x. I'm totally, yeah, I may be totally wrong about this. But if it is, then we can collect the like terms. Get 2x equals 3. Hmm. Hmm. Doesn't seem that satisfying. No. Clearly the wrong way. But it's like the minimum of this. So 1 plus 2 times 3. Does that get us the answer? So 7. 7, 6. Well, it takes 6 steps to get there. So, we can subtract 1 off of that because we don't count the last one because the last one's already there. So, in theory, yes, theory, this works. Should I add another example? Do I? No. Okay. Fine. So we just have to do several difficult things. I noticed the pattern was there. And there's really no way to because of the alternating nature of the because of the directions, you can't just take it sort of simply and say if you see the same cells in the same order, then you get the right answer because you might be in a different state at that point. You might be following different directions. Okay. But how predictable is this pattern? Does it have any repeats in it? Yes, quite a few. Okay. So what are we going to do now? Am I going to take some time to think about this and puzzle it through some more? Or am I going to make an attempt now? What I really need to do is as we move around the as we take each point and we move on from it, I need to be able to detect when we're in a cycle. So I guess, ah, maybe we could model this so that I'm just trying to think if we can include the direction in the cell, but I'm not sure that's the right thing to do. So the problem is Okay, let's go with the ugly version of it. If we are on a cell with the same if we are on cell X with OSC index Y, and we've seen this state before, we can we're in a cycle. And this may not happen for a while. What I'm worried about is that it could be that that doesn't happen for a long time. And therefore it takes us a while to figure out. But if that does work, so the maximum length of a cycle then is going to be the length of this, which is 282 characters long. Multiplied by the length of the graph, I think. So it's 796 times 282, which is 224,000 or so. So that's I think that's the maximum length of any period, which is not so bad. By that point, we I believe should have seen the same head, the same state. And then if we can get that, we'll be able to get the cycle length. And if we can multiply those out, then we win, I think. So that does seem plausible. So I think that approach seems like it might work. We're only going to know. So in fact, we're going to need to double that really, which is it's not a big problem. So if we're on something that ends with a Z with oscillator index Y, and we've seen the state before, we're in a cycle. So what we want to be able to do is to determine the cycle length between Zs and Zs. And they could also be offset, right? So yeah, okay. So when we see but we could visit multiple Zs, and it's not that everyone's going to have its own Z as well. God, that's a nightmare. Oof, difficult day. Yeah, so we're not guaranteed that these are. We're not guaranteed in any way that these are. Okay, so I've got CJZ. Is there a CJA? No. So there could be totally different Zs. So in fact, we need to track, we need to track, um, we need to be able to get, all right, okay, let's look at it this way. Okay, so we start off with, in this one, we start off with 1, 1A. Start with 2, 2A. Okay, all right, well, maybe this makes it simpler. So here's what I'm thinking. What if each cell, let's go with each Z cell has a dictionary in it. And the dictionary is keyed on the index of the key, the index of the pattern rather, the index of the oscillator. Yeah, the index of the oscillator to the next Z that it touches after that. And as we go through, we keep track of these. So when we hit a Z, we know the last Z that we hit. And the index that it was on at that point. And then the next time we can skip ahead to that point. And then we hope, I guess, that there are few enough of those combinations. Yeah, okay. So I'm going to make a plan, then take a short break, and then come back, do some coding. Okay. So yeah, well, that helps us somewhat. That helps us somewhat, but then we need to Then we need to do some fancy logic to make sure they all, because they're going to be different periods, aren't they, for each head? So we need to do some fancy logic there as well. I'm going to take a short break, I think. Okay, so I've got a bit of a plan now. Here's what I think. So what I think is we can keep track of whenever we see a Z. So whenever we see a Z cell, we can keep track of, we can sort of start saying, okay, we've seen 22Z. Let's keep advancing. And the next time we see a Z cell, we will add a record to a dictionary saying, if you're on this Z cell and you're at this point in the pattern, then you can skip ahead X steps and you will be at this Z cell. If we can then do that, and implementing it takes a little bit of funny logic because you've got to then just make sure that you don't skip too far ahead with different heads and all that sort of stuff. If we can do that across multiple heads and also keep our logic to do with incrementing, just stepping once, then hopefully we get a reasonably efficient solution where we're skipping most of the work. My algorithm is sort of a little bit complicated, but essentially what we do is we go through, we check not all the cells are winning cells. We go through each of one of, n heads. We advance the head. If the cell ends with Z, we say, okay, this is the last Z cell we've seen at this steps. And we keep going until we see the next Z. Once we do, we add it to the skip dictionary. And if we then see that cell again, we mark the head as skipping and how many cells it's skipping for. And then if we're in a situation where all the heads are skipping, we subtract the minimum of the skips across all the heads and add that to the amount of steps. Then we would, in theory, we get to the right answer. A little bit complicated. So I'm a bit worried I'm going to make several mistakes in doing this. Probably no easy way to avoid that other than being careful and making sure I've got lots of room for tests. So we'll see how it goes. In terms of a plan of action, there are a few things I've got to do. I'm going to redo the state entirely. Remake compute to get all of just produce all the new heads. Write the new advance and steps to end should say the same. Who knows? Let's try it out. I think it's time to start doing some coding. Okay. So part 1 into part 2. I'm going to save this trial here. Oh, not in there. Okay. My input is the same. Stop this going. Set the timer and get going. Okay. Let's go with a string for that. Okay, that's fine. New state. Still going to have an oscillator. It's not going to have a start or an end. Current. We'll still need that. These tests are going to need to be rewritten. The oscillator's still there and the skips. It's a really messy data structure. Okay. I'm going to keep this. I'm going to keep this just around, and then I'm going to yeah, I'll come back to that. Okay, so we've got this, yeah, fine. We need the cell dict. Zero, one, two. Then we've got a new head. I actually need that at all. Okay, we've got our heads there. Now we need to write our new advance. This will be the horrible part. Okay. No. Uh, hmm. Yeah, I'm gonna need to have all this in one, I think. Okay. Probably a more efficient way to do that. Okay. Okay. Actually, that will never be always true, I think. Um, hmm. Let's keep going with the plan. Just a lot of things I'm not certain about here. What is it first? Int first. Okay. Gosh, this is very tenuous. Okay. Well, it's actually now this, isn't it? Let's keep those separate, just for certainty. Okay. So at this point, we're definitely going to have at least one, well, at least one head that is going to start skipping. No, at least one head that either needs to be advanced or is going to need to be stepped. So in theory, we could move down this down here. And then otherwise, we move to the stepping logic. And we use this logic. If this works, I will be absolutely, well, it's not going to work, basically. 97. Six steps. All right, well, it works in the small version. Let's try with the input. Nope. It should all be mapped at this point. Oh, there's no current. Why would there be no current? Can't print the head because it's too big for some reason. Maybe this is trying to print the cell. Okay, so it's getting through to, it's getting down to, oh, okay, fine. Yeah. Now it's looping forever. Where's it hanging? Where does it store? It's infinite looping somewhere. Because it's in the skipping logic. Yeah, so it gets to the all skipping logic and then it loops forever. So in theory, we can advance based on that, right? We just need to find the we multiply all these together. Add this. Probably get some, yeah, ridiculously high number. Not scientific number, please. Assuming that they all have one, assuming that the next, well, in fact, we can check this out, can't we? Yeah, they're all the same, right? They don't change. Yeah, so in theory, that's the answer. I bet it's not though. Nope. It's too high, is it? Yeah, thought so. Hmm. Okay, so it's not that. The code. Well, it would be interesting to see if we do change this to product. Does it actually terminate? No, it doesn't. Maybe there's some, because in theory that should definitely yeah, I mean that should get us to all Z. So what are we actually getting at that point? Oh, no, come on. Well, that's the new one. If we just skip with the product, then we get to this final point, which I'm not super convinced by, but let's try it. Too high again. Let's go back to the minimum logic. Let's take a closer look at this. You know what I'd be interested in? I'd be interested in the contents of the skip dictionary. Hmm, the wrong way round. Yeah, we want to go from the last Z cell to the current cell. Yeah, the product again. It's the same one, same thing. Too high again. The oscillator index is always 0, though. And they're always going in a loop. So if these are right, which they should be. Why is the oscillator index always 0? Is that just a coincidence? I'm not advancing it, am I? Yeah, I'm always advancing it. Otherwise, the other one would never work, right? So in theory, the answer should be in here. And it should be they're all going to be the same, right? We've got 0, 1, 2, 3, 4, 5. No, that's 6. 1, No way. That's not gonna work. How do we check if all of an item is the same? Oh, I've not been recording myself coding for the last ages. Sorry. What a nightmare. I mean, I really do think it should be all these multiplied together somehow. Well, that's a different answer. We may as well give it a go. Too high again. That's even higher. Oh, hmm. Maybe is there a common factor of these? Is this going to be fast? I have no idea. Right. This times one of them plus this. Is it here? No. All right, let's try that. Hmm. Run out. Run out. Run out of numbers. Run out of guesses. 5 minutes. Okay, 5 minutes from 15:03. Well, this does at least give us something to think about. All right, so if we have n as this, well, they're still all different. But this is the lowest common multiple of all of these. Or maybe I'm a step off. Okay, so this number definitely, yeah, this number definitely goes into all of them. And it goes into them all those number of times. So if n is this, we still get different numbers. But we need to adjust for the fact that they're offset, right? Sorry, I'm still not recording properly. Okay, let me put this another way. What we would like is for to solve this equation. Now, if we can reduce this by taking away this from both sides. To make 10, 1, 1, 6. And then taking away this, well, this from both sides. Oh, God, why? Why? Sorry. 5058. Pretty sure x should not be negative. Okay. So, but in theory, the logic is right, isn't it? So let's say that we want to find an x where these, let me write this out. This is going to be steps. Yeah. 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 So we're at a z whenever this is true. And then we're going to have the same deal with this. And here. So here. So all of these need to be equal. Now, I can go another step with this. I can put all these in terms of x. That's me. That's not helping at all. If I put this in terms of x, I can put this in here. And get this. Add this to both sides. No, that can't make sense. My algebra is not good. But I know this can be solved. What am I missing here? I want to find the intersection, right? It's like the other day. I want to find the intersection between each of these. Say they're all equal to each other. There's a formula for this. Okay, so we've got to do it with 6 equations though. Let's try it with 2 to start. Okay, so ax plus b, cx. So the formula is, given this, we can do this. So x equals e. No, wait. E minus b over a minus c, which is minus 2. C equals minus 2. How can x equal minus 2? Um, so in this case, we get, well, we get 0. That's not that good. In this case, we also get 0. Keep calculating, I suppose. They're all coming out as 0. What's wrong here? Have I made some sort of horrible mistake in my code? These are just half. That's very suspicious. I'm beginning to suspect all this might be wrong. Yeah, these are just halves. This video is going to be of no use. I'm going to stop it now. So we got the right answer in the end, though not. It took me a while to figure out why I got the right answer. There are a few things that are sort of basic. The basic approach, as it turned out, was broad. In fact, let me get my diagram up. It was broadly this. Broadly, we're looking for cycles that the heads experience as they go through the graph. And broadly, this algorithm like works with a tweak that once we find the length of the cycle, then we can find the least common multiple of all of the cycles, and then that is essentially the answer. There are a few coincidences that make this a little bit easier than it would otherwise be. I don't know if they are actually coincidences or if they are somehow genuinely built into the problem in a way that there couldn't be, it couldn't be otherwise. So let's look at those. So the first thing is where we first find so what I'm looking for is have we seen, so has any of our heads been on this ending cell at this exact point in the left right sequence before? And if so, how many steps ago was it, so that we can just repeat that out? My suspicion was that that each head might encounter multiple possible ending cells. So it could be CJZ, then SNZ, then CJZ again, and you would have to keep track of multiple possible ending cells. So you couldn't have a simple, we're going to see CJZ every 12,083 cells, every 12,083 steps, and no other ending cells. As it happens, there are a few things that make this, that allow us to jump to the solution. And this is my suspicion. I may be wrong at some of these things. So firstly, what you'll notice is that we encounter the ending cells always at the start or the end, depending on how you look at it, of the left, right, left, right, left, left, right sequence. It's always at the same point, it's always at the start. So we don't have to worry about encountering an end cell halfway through our sequence, which simplifies things because we don't end up with things that are sort of out of sync. Second thing that makes it a bit easier is this: no head encounters more than one ending cell. So you don't get CJZ, then SNZ, then CJZ again. You don't get that sort of thing. You always only encounter one. And thirdly, the space between the ending cells is so if you look at what this number is, you'll notice that this is a double of this. What this means is I started at my starting cell, the A cell, and I have gone 12,083 steps, and then I've seen CJZ, and then I've gone 12,083 more, and I've seen CJZ again. So the distance from the starting cell to the ending cell is the same as the distance between ending cell and ending cell. All of those things mean that we get to make a jump in the solution, which means we can use this math LCM thing, which will work out I'm sure there's an algorithm behind it, so some of you had to implement. But we were able to essentially find the lowest common multiple of all of these skips here. And that was the answer. Now, I'm not 100% sure. Maybe built into the problem, maybe built into graphs, these features are sort of inevitable. You could never have, things drifting out of sync. You could never have them visiting multiple ends at once. Maybe that's true, and I just don't know enough about graphs to say. But it surprised me that there were a number of things that sort of coincidentally helped us towards the solution there. In any case, I ended up getting some very large, very large outcomes, which is undoubtedly my own fault, and in fact a very low one as well. Undoubtedly my own fault through quirks in the algorithm that I implemented that was incorrect in some ways. I'm not 100% sure exactly how it was incorrect, but in fact, you know what? I think potentially my algorithm ended up too slow as a result of all the edge cases that I thought were going to be there that weren't. Anyway, I'm not certain. Probably I'll look back on it. No, I probably won't. Got the answer today, but I'm not like super satisfied with how this went. Of course, it's a later on as well, but I'm yeah. I mean, I got the answer, but I didn't have to look it up. But yeah, it felt a bit magical when I got it. Anyway, that's that. See you tomorrow.